is Yago Antolin from the Autonoma University in Madrid, who's going to talk to us about convex subgroups of orderable groups.
Well, thank you, Martin. Thank you everyone for coming. I've been told that it's one of the greatest honors to be the speaker in the morning session after the conference dinner, because that means that the organizers are confident that you will attract enough people, so we can start well the session. So yeah, I'm gonna talk about orderability and convex subgroups, and so we will see a bit the connection with non-positive curvature later. But I guess that the main thing that we are doing is doing things that they should have been done like 40 years ago or things like that. They're like, well, there's going to be some theorem that it should have been known for a while, and we think that it's useful, and well, we will reach at that point at some point, I hope. So it's going to start very basic. What is orderability? Well, G is orderable if it admits total order invariant under left multiplication. So really you usually call this thing left orderable, but to not be saying left all the time, I'm just going to say orderable in this talk. And a subgroup is relatively left convex, but again, I'm not going to put left, if the cosets admit a total invariant order, total order invariant under the left multiplication. So why I'm saying left or relatively convex? Well, because I'm not assuming that the whole group is convex, and what you have to think is that well, if you have some total order, that means that you can put your set in a real line, and you have some cosets that has been ordered, and once you order the subgroup C, okay, that is relatively convex, suddenly the whole thing is convex, because you have ordered your cosets and then you order your things inside, and this is going to be orderable. Okay, so what I'm saying is this group is relatively convex in G and orderable, then G is orderable. And probably I should state a lemma. It's not something very classic, but just to see why the name convex is coming from. So suppose that this is total invariant order on G. So this thing is convex, or relatively convex if and only if, with respect to if and only if for all A, B in C, and for all B in C, in G, if you have something like this implies that B belongs to C. So I said that this is a lemma, and okay, that seems more like a definition. Okay, the lemma, I guess, it should be that you are relatively convex in an orderable group if and only if you are convex for some order. Okay, so just to clarify, C is relatively convex in an orderable group if and only if C is convex for some okay. So let's do some very basic examples. I think the first and main one is the integers. This is orderable. It has two orders only, and in both of them the trivial group is relatively convex, and also the full group is relatively convex. And orderability is preserved by subgroups and direct products. So you can see that then you have that C to the n is orderable. So subgroups is clear, you just restrict the order. Direct products, you just put the lexicographic order in. You order each of the factors, and then you put the lexicographic order. So a product of groups is orderable, and any maximal generated subgroup of C to the n is relatively convex. It's going to be convex for some order. Okay, why is that? Well, because if you take a maximal k-generated subgroup, the quotient is going to be C to the n minus k. Okay, and then that's orderable, and that was the definition of being relatively convex. Okay, and I guess, well, probably you all know this thing, that orderability implies torsion free. So this gives you a bunch of non-examples of things that are non-left orderable. And I guess a characterization of orderability that may help you to find more orderable groups is G is orderable if and only if G acts on a totally ordered set by order preserving transformations.
Yes, faithfully.
Faithfully, yes. Faithfully. Thank you. I think this is the action. Okay, that's my first stage of basic things. So, yeah. So what I want to talk now about is other constructions that preserve the orderability and that's free product. Okay, so when we have free products, we can order the free group, which is nice. It's a group that everyone loves and likes. And this is something that has been known since the 40s. I have some names here of people that seems that they know how to order free groups. Seems that Tarski knew it, Birkhoff knew it, Iwasawa knew it. And usually the reference is given to Vinogradov. But, well, the thing that happens is that all these proofs or all these constructions either are give orders that are non-explicit, or even if they give explicit orders, they are difficult to work with them. Okay, so that's something I particularly don't like. So just as an example of how you do such a thing, there is a beautiful argument of G's that says that if you take two random elements of the group of homomorphisms that present the orientation of R, they generate freely free group. Okay, so R is a nice ordered set. You are acting there, so the group that you have is any subgroup there is going to be orderable, and if it's a free group, then the free group is orderable. But definitely, this is not the way you want to prove that your free group is orderable, because then how you describe this order. And I guess if you want to say, okay, but why do we care? I mean, there are many reasons to care about orderability, but maybe orderability of free group was important or was key for the Hannah-Newman conjecture. At least if you follow what Minayev did, he really needs the extra structure of being orderable on the free group to prove the Hannah-Newman conjecture, and just to give some self-publicity, Hannah-Newman conjecture for free products of orderable. You can also do this thing, and that's something that I did with Martino and Ingashawa. So this extra structure, it might help you to do things. Okay.
Yeah. I believe this then, but what's random mean?
Okay. There's some topology there, and basically there's an open set that. Yeah, that's in that sense. Okay. So I'm going to tell you about how to order the free group in the way that 2 years ago Dix and Sunic did. So I believe that the story is that after we have the solution of the Hannah-Newman conjecture by Minayev, I don't know why, but Sunic got really interested in ordering the free group in an efficient way, and he started producing different orders. And well, later he teamed with Dix, and they, well, I think that they give a really nice explanation and why the free group is orderable, and it uses geometry, uses the negative curvature of the free group. So let F2 acts on a tree or its Cayley graph. Okay, and what they do is, okay, so the Cayley graph is going to look like this. Locally, say A, B, A, B. And what they do it says, okay, just put some local orders on the vertices. So local order on vertices. So say that this is your first vertex, second, third, first hertz, second, third, and fourth. Something like that. So this is bigger than this is bigger than this, and 3 is still bigger than 4. Okay, and do it in a G equivalent way. So the link of every vertex in the tree looks like this, so that means put exactly this order in every vertex of the group. Okay. So now we said that you are orderable if you act faithfully in a totally ordered set by ordered perceptive transformations. So what they did is they ordered the tree. Okay, so if you order the tree, the free group is acting there nicely, so you will end up ordering the free group. So we construct an order on the vertices of T as follows. So I'm going to say that U is less in the tree than B if and only if, okay. So this is the path from the reduced path from U to B, and this is a function. So I need to tell you what is the function. So the function, what it does is it counts the vertex rises of P. It subtracts the vertex falls of P. I will explain this in a second. It will count the number of positive edges and subtract the number of negative edges. So this is very informal, but you will see it in a minute. So
Are you asserting that those things are roughly the same, or are you asserting that it does both of them? Are you asserting that it roughly does both of those, either of those things?
no, it's okay.
Or is there some?
If there's some. Thank you, Henry. So what this is doing, so if this is my path P and I have a vertex here W, if this, say, E is less than F, so if I move into a bigger vertex, bigger edge, this is a vertex. So it's growing on this vertex. Equivalently, if you have that E is less than F when you are going in this direction, this is a vertex fall. And again, we are going in this direction. So if you cross an edge in the positive direction, this is a positive edge. And if you cross it in this way, this is a negative. Okay, so that's all. And we can do maybe an example to see how this really becomes something very easy to compute. So I don't know, if you start from the identity, do A, you do B, you do inverse. Well, with the locals orders I have there, if you go from A to B, you are racing. So this is here you have a +1. If you go from B to A minus 1, you also are racing. So you have a +1 here, and you are going in the positive direction in this edge, in the positive direction of this edge, and the negative direction of this edge. So this is, I believe, this is positive. Did I put? Okay, I guess equal and equal. Okay, that's good. So you're saying that this vertex is smaller than this vertex, and you can say the same thing for the group elements. Okay. So, well, some observations. If you consider the path from a vertex to itself, that's equal to 0. So that's good. That means that u is less or equal to u. You can see that if you reverse the orientation of the path, then you just change the sign, okay? And well, if you just multiply your vertices by something, well, you are just moving your path, but it looks exactly the same. Okay, so this is invariant under G, under the G action, and I guess the only one thing that also is clear is that if this is equal to 0, if and only if u is equal to v. And why is this the case? Well, that's because you will end up always adding an odd number of 1s or minus 1s. Okay? If you have, in this case, a length 3 path, you have 3 edges, but you have only 2 vertices. Okay? So in a length n path, you have n edges and n minus 1 vertices. So at the end, you are adding an odd number of 1s and minus 1s, so you cannot get 0. And so that's why total orders the whole thing. Everything is either positive or negative. And I guess the last thing one has to check is the transitivity. Okay, if A is less than B and B is less than C, then A is less than C, and that, well, you can do it with a picture. It's just the cancellations that you have with 2 paths in the tree, and well, one of the things that you can get is that and it will follow from this identity, the transitivity. Is that if you take 3 points, this thing is always less or equal to minus 1. Okay. I don't want to go into the details, but probably Alessandro is thinking this is a quasimorphism, no? Of this. Yeah, this is a quasimorphism. In fact, the previous works of Soran, he produces orders on the free group using quasimorphism. Okay, so let me just move to something. I have some contribution. So the whole trick of ordering the tree is that, or ordering the free group, is that you act on a tree and that you can put some local orders on the vertices. Okay, and you can put them because you are acting freely, so put any order and it works. If you are not in a free group, if you are not acting freely, then you have to be careful about the orders you put here. They have to be invariant under the action. Okay, so then you think, well, if I'm in if the stabilizer is an orderable group, I just use the order I have to put the local orders on the vertices adjacent. But maybe I have some stabilizer of the edges. Well, in that case, I know that the link of this thing is going to be the stabilizer of the vertex group modulo the stabilizer of the vertices, and I need to order this link. And if I am ordering this link in a G-covariant way, basically I'm saying that the edge group has to be relatively convex in the vertex group. So, so just with the same construction, we have that if let's just do something concrete, but this works for any graph of groups with C relatively convex in A and in B, then, well, you can do the proof I just sketched for this group acting on its master tree, and what do we want? Well, you get that A and B are relatively convex in G. Well, that's because they are stabilizing some vertex, and you have G acting on the causes that, well, I mean, they correspond to vertices of the group, and this is going to be ordered by this ordering that we constructed. If C is orderable, we say that if C is orderable, then you can order A and B in a convenient way. So you have that G is orderable. And so these two things, they were known. Okay, it's like we knew that the free group was orderable. We knew that orderability was preserved under this type of constructions. But the new thing is that if the orders of C and if these orders are given efficiently, then the order on G is I don't know, is explicit. Okay. I mean, you can construct an order basically as good as the input order that you got. So what does it mean to be as good or as bad? How you measure goodness or badness of orders? Okay, I guess there are different interpretations, but one way of defining an order is by what is called the positive cone. That is, just give me the elements that are bigger than the identity. So giving an order is the same thing as giving a positive cone. And a positive cone has to be closed under multiplication by itself. Okay, and the thing is, P union P inverse has to be P union P inverse union the identity has to be the whole group. So you can think, okay, it's as difficult to give the order as it is to describe the positive cone. And so for the free group, the order given before, positive cone is a context-free language. So I don't want to go into details. If you know what context-free is good, if not, it's a shame. But basically, is that you have some automaton that is very simple, and you need very simple memory to compute things. Okay, and you definitely need some memory because you need to go counting plus and minus ones. In C, for example, you have a positive cone that is a regular line, which is much simpler. And there is a theorem that I really like of last year of Sunic and Hermiller. I guess the other way around. Well, and you cannot do it better. Meaning that if you construct a positive cone for a free group, it will never be a regular language. Okay. There is no way to construct some order that is simpler than the one I just gave you. At least from this point of view of languages. Yeah.
So in the free group, it wasn't just a matter of the local order; it was the order on the lines in the tree as well. So how does that? So the counting the direction of the edges. How do you do that in your theorem?
Well, I mean the same way. You know, I mean you have a graph of this thing. You construct the tree, and edges will have some orientation, and between 2 points. What you usually do is you just add some edge and a vertex with a trivial stabilizer. So suddenly you have one vertex for each element of the group, and that's how you do it. But it's
you don't have to worry about lines being flipped.
Lines being flipped,
and there might be.
Okay, you mean that this doesn't? I mean,
No.
there's some G.
That doesn't matter.
Okay, yeah, I don't. All right, let's move to more things. Okay, but now if you see this theorem, okay, you say, okay, well, nice. I can construct new orderable groups if I know how to find convex subgroups. Okay, so how to find convex subgroups? Okay. So let me remind you some old theorems. It says that if for every non-trivial finally generated subgroup H of G, H maps onto an orderable group, then G is so to prove orderability is really a local property. It's something very thin. It's something that if you perturb a bit the group in the small scale, it just can disappear. And there is this theorem that exploits that and tells you that you only need to look for finally generated subgroups and see if they map non-trivial also, and see if they map into a non-trivial orderable group, and then you will be able to put all these orders together to order the whole thing. And I guess a corollary that I like is that if G is locally indicable, then G is orderable. Locally indicable meaning every finally generated non-trivial subgroup maps onto C. Okay, C is our ordered group by excellence, I guess. So there is this theorem that allows you to show that many groups are orderable. In fact, the first proof I knew about the free group being orderable was through this corollary, which is definitely non-constructive at all. And these guys, they should have proved something more stronger, because more or less these ideas, they allow you to show that subgroups are relatively convex. In fact, what they are proving here is that the trivial group is relatively convex. And okay, there is a version of this theorem that is a bit more general, or a generalization of this theorem that is a bit more general, but let me just put it in this way. So fix some subgroup, and if for all subset of G, for all finite subset of G, you have that these maps non-trivial orderable group. So I guess I need this thing to be non-trivial. Well, then G0 is relatively convex in G. Okay. So I need this, well, I need this to be non-trivial. Okay, if it's trivial, then I cannot map into a non-trivial thing. I mean, the statement should be a bit more general than this. It should be like the analog of this thing, that would be that for every relatively finite generating subgroup with respect to G0, it maps onto an orderable group in where G0 is convex. Okay, and I'm writing it this way because I'm just saying it maps trivial G0 maps into the trivial group, and the trivial group is always convex in an orderable group. So that's something that I think it should have been known for a while, and it allows you to show that many things are relatively convex, and also, well, in the same way that you could instead say maps onto an orderable group, you can say maps onto C. You can change that and have some corollaries. So we have some classes of groups that probably are much nicer, and it's generalization of local indicability. So we're going to say that G is n indicable if it maps onto the n, or it is generated by fewer or less than n elements. Okay, so it's the same thing. We had indicable, which is one indicable, means that either you are trivial, okay, generated by less than one element, or map onto C.
About the last theorem, does it say that G naught is relatively convex if the normal closure is?
Hmm?
Does the last theorem say that G naught is relatively convex if the normal closure is?
That's what I'm saying. This is
That's trivial because it's yeah, okay, no.
well, and this is not the best statement that we
Yeah,
could
no,
have.
no, I understood that. I just
No, I mean there's nothing to do with normal closure. I mean no. I mean there's something to do in the sense that that's written a normal closure, but that. No. And then a group is locally n-indicable if every finally generated subgroup is n-indicable. So examples of these are free groups are locally n-indicable for all n. Orientable surface groups are locally n-indicable for all n. Okay, because I mean, if you have infinite index subgroups, you are free, and that's good. And if you have a finite index subgroup, you are again a surface group, an orientable surface group. And the good thing is that a velarization of this thing is the rank of this subgroup. Okay, so there is I guess this is a proposition that we prove that locally, but well, residually torsion free nilpotent groups are two locally two indicable, and I think this is rags are not locally and indicable for all n. So this is an example. There is an example that is in a paper by Ashot Minasyan that says that it's an example by Martin Wrightson, who gives some finite index subgroup of F2 plus F2 that will fail being n indicable for some n. I don't remember which n it was. Okay, so this is a class of groups, and we want the equivalent of that corollary. And what would it be? Well, you take any finally generated subgroup, and then either it's generated by fewer than n elements, so you don't care, and if it's generated by more elements, then it maps into C to the n, and we know that any maximal subgroup there, I mean C to the n minus 1 will be convex, so that's that's good because you kill that, and it's gonna be going to something trivial. So let me just write the corollary. So now it makes more sense what I'm saying. Let n be or equal to 2 if G is locally n indicable, then each maximal n minus 1 subgroups are, maybe I say it again. So you have a maximal n minus 1 generated subgroup, and you add something. Now this should map into C to the n, okay, and you can kill everything except you can kill the part that is mapping into the C to the n minus 1 part, and you have a map onto C which is order.
So maximal n minus 1 generated subgroup means maximal among n minus 1 generated.
Yes, maximal among n minus 1 generated. Yeah. So in particular, maximal cyclic subgroups of free groups. And I guess why I'm saying this, because I mean, you, in the same way that you care about the free group being orderable to prove these sort of things, I think that here in their paper, they care about maximal cyclic subgroups being convex in the free group to show the what is this W conjecture? W conjecture?
The W cycles.
W cycles conjecture. So you have a free group C maximal cyclic and H subgroup of F. Then you have like some sort of version of the Hahnemann conjecture, but instead of using reduced ranks, just using ranks. And you have that the sum over the double cosets. Oh, let's put rank. And it's important here, at least in their proof, that you can order F modulo C. That there is some order there. I mean, you are using.
Yeah, we're using something like that.
Just okay. How are we doing on time? Okay, it's good. So I have some more examples, and basically it's in the same vein of this. So let me just put at the definition. I don't know if this is a good term or not. G is Nash-Moff. It means non-abelian subgroups map onto a free group. If G is torsion free and non-abelian subgroups map onto F2. And well, here you have free and free abelian groups are Nash-Moff by definition, and the interesting thing is that residually free groups have this property, and this is a theorem from me and Ashok Minasian that ranks are so they are not locally n-indicable, but they have this other strong property, and that's a non-trivial result. And well, in the paper we call it the strongest least alternative. I mean, every non-abelian subgroup maps onto F2 is like the strongest possibility that you can have. So you can play the same game that we did before with this corollary. So now you take any finite generated subgroup, and you know that it will map onto a free group unless it is abelian. And you know that, for example, if you try to map an abelian group into a free group, you have to send everything to an abelian subgroup that is cyclic or trivial. So as a corollary, for all n, G Nash-Moff, then for all n, every maximal n generated abelian subgroup is relatively convex in G. And well, this tells you again more many other subgroups that will be relatively convex. For example, in a limit group, you know that it has is relatively hyperbolic to its maximal abelian subgroups, and these groups are in particular convex for some order. Okay, and we have all this list of examples in this family. Okay, this is the end of my notes, so I think I can stop here.
Thank you. Retain the tradition of timely ends to lectures. Have questions?
You know if the orders you get, say from the free group, are in some way dense in all of the orders possible?
Well, the orders on the free group, the ones that we get, they are not, because I mean there are uncontrollably many orders on the free group, and this is going to be something. I mean, you're not going to be able to get no. I mean, I don't have the right argument, but no.
You said dense, right? I mean, probably if you looked at like bigger balls rather than just the ball of radius 1, you might be able to. I mean, probably. I say probably. I have no idea, but
okay. Well, let me try to think and say something wiser.
Anything else? Let's thank Yago again.